Yeah. Okay, Michael, go ahead, please.
Okay. Right. Well, good morning, good afternoon, good evening, and welcome to all who are joining us for this second talk in the OSMU series for 2024. And our speaker today is Basil Hiley, who is indeed the second speaker for our series last year. Basil was born in India in 1935.
I beg your pardon. Please, I was born in Burma. Please get it right.
I beg your pardon. I'm so sorry, Basil. My apologies. I stand corrected. Okay, you've thrown me off my stride there. I apologize. Okay, born in Burma in 1935. And he's told me that I think the very earliest algebra book, which is still on his shelf, was one that he had, which was a high school algebra book, actually printed in Kolkata in 1943. So, you know, he cut his teeth on algebra textbooks in India. But he came to London as a young man, and after pursuing his degree at the University of London, he joined the department at Birkbeck in 1962, where he became assistant to David Bohm. They worked together for some 30 years until David's death, and together published a great many papers and one major book, The Undivided Universe, which appeared in 1987. Since then, in the second half of his career, Basil has continued to work in a very bold and very original way on, particularly on alternative views of the quantum formalism and of the conceptual structure of quantum theory, centered particularly on the idea of the quantum potential. And he has contributed, amongst other things, a very interesting paper to the book on new structures in physics, edited by Bob Kirker, which appeared about 10 years ago, entitled Process, Distinction, Groupoids, and Clifford Algebras. And it's more about the work, the direction which that work has taken, and the very considerable further extent to which the ideas already in that paper and published elsewhere have continued to be developed, that he's going to talk to us about today. So with that, thank you very much, Basil, and we look forward very much indeed to hearing what you have to say.
Thank you, Mike, for the introduction, and thank you and to Jinder for inviting me to present a talk to this very interesting series of lectures. And I want to start straight away by really reminding everybody of the conclusion that was reached by Roger Penrose in his talk a fortnight ago. You remember he actually argued that because there was a conflict between general relativity, i.e. the principle of equivalence, and quantum mechanics, the linear superposition, that the contradiction meant that there must be two realities, a classical reality and a quantum reality. And I, in fact, already raised the question of whether that was necessarily true. Now, what he did was he used the Schrödinger picture, and all the time dependence in the Schrödinger picture is in the wave function. But I will use the Heisenberg picture, and I will conclude that there is only one reality. Now, remember that underlying these various pictures is a very important Stone-von Neumann theorem, which proves that there are a number of pictures which are unitarily equivalent. So they're mathematically equivalent, but they're not necessarily physically equivalent. And I want to just develop the Heisenberg view, not from the way you learn in particle physics. I want to look at it through the eyes of Clifford and Dirac. And remember, the whole point about the Heisenberg is that the time dependence is put in totally in the operators, and the wave function just sits there doing nothing. And I often wondered, why is it? It's dynamically redundant. But how do you do the operator calculus? As I say, the real clues are in Clifford's work, and this was the last book. It was written posthumously by for Clifford, in which he created the algebra, which is used in Pauli and Dirac, and as a marking earlier on, in modern robot theory. Okay, so let's go right back to the beginning. And remember, the problem was, how do you explain the Rydberg formulae dynamically? You can do it quite easily using the Bohr's frequency condition, but how do we do it dynamically? And Heisenberg introduced an ansatz. And the ansatz was that all classical variables could be written in the form of a polar decomposition with the amplitude depending upon an index of two symbols, as well as the frequency. And all the dynamical variables are written in that way. So that means that if you now square the classical variables, you've got to have a product between the two polar variables such that it produces this. Then you find the Rydberg relationship is satisfied automatically, but it gives a different type of product for the amplitude. And the amplitude just simply, it looks like matrix multiplication, and it just simply adds over K. I haven't got the summation over there. I've just got the bare bones of the idea so that we can see exactly what's going on. Now, some of those transitions are forbidden, and therefore what we're dealing with really is a groupoid. And this was pointed out by Alan Kohn in his book on non-commutative geometry. And I'm going to lead on to non-commutative geometry, which plays a very basic role in everything I'm going to say. And now what I want to remind you is that we can also look at the momentum squared, which has a star product with the amplitudes. And it's this that leads directly to the quantum potential energy that Mike remarked about in his introduction. And just remind you that in relativity, your inertial mass is always in terms of the rest mass, the kinetic energy, and the remainder. And we always throw that away at the classical level, but we throw it away at our peril at the quantum level. Okay, so let's have a look at groupoids and see what the algebra is. And it's the algebra of what David Bohm called the structured process. And we keep everything discrete, and we'll go to the continuum later. And in order to simplify the notation, I am going to replace the Heisenberg ansatz with just this symbol, P0, P1. And I'm really following Clifford here, and I'm calling this symbol here a step, so that we have a step, a source, and ends up as a target in the groupoid language. And I also discovered that Cartan writes for this, he writes dp, and he means delete P0, tail of the vector, and create P1, the tip of the vector. So you're looking at the step as it used to be called a versor, but that term has gone out of use, and I have to call it a velocity vector. Okay, then Clifford introduces a new process. That is a spinning versor, and that's what he called a rotor. And the rotor actually is confined somewhere along a line and has a spin associated with it. And the rotating vector, in fact, is just the quaternion. And if you write it in this particular form, which is written by a great friend of mine, Ed Pintz, in terms of two complex planes, a complex plane which he calls CA, which provides the number, and a two-dimensional plane. And hang on, and you can see the two-dimensional plane in terms of perpendicular to this. So you're thinking really of something spinning. So the rotor is something which is spinning, and the classical examples of rotors in classical work, you've got the skaters, you've got the old Indian tops I used to play with, and you've got robotics. But you've also got them in quantum mechanics. If you look at the molecular spectra, what you find is for just very simple carbon dioxide or water molecules, you have vibrational degrees of freedom and you have rotational degrees of freedom. And they they occur at different energies. The easiest ones to excite are the vibrations, and they're down here. So the vibration energy is down here. If you then get the molecule to rotate, the actual vibration energy changes, and it changes by what they call here the Coriolis energy. So the Coriolis energy is actually seen quantum mechanically in the molecular spectra. So it's not only a classical situation, it's a quantum situation as well. Okay, the next thing that Clifford introduces is the idea of what he called the motor. And the motor is really a change of one rotor. So we'll draw the rotor here, and we convert it into the rotor AP. And that rotor is really moment plus rotor. That's where the name originally came from. Okay, but this is where we describe it by the biquaternion in modern language. And it's an element of the Dirac-Clifford algebra, which is a 16-dimensional algebra. I use the word Stonian here because that's what Schouten called it in the 30s. And Schouten has done a lot of very interesting work, which again is not in the popular literature for physicists. Now, all surprisingly, the Penrose twistor is simply a motor, because you look at the light ray, it's two light rays here, and the light ray has angular momentum associated with it, a spin, and you take a moment of the two light rays and you describe it by means of the brilliant work that Roger has done over the years. And what we are going to do is to build our structure process from a collection of fundamental movements. So we're not talking about objects, we're talking about movements, we're talking about process. And please remember, which is what Clifford did not do, was that the steps require the expenditure of energy. In the early work of Clifford, you don't see energy appearing at all. And yet energy is absolutely vital to the story I'm telling. Okay, now looking at this symbolism I've got here, we can introduce a projector S, which projects out the point P, and T, the target, which projects out the point P. And what we say is that the multiplication defines the order of succession. So you make one step from P1 to P2, you then make another step from P2 to P3, and you just eliminate P2 and you build up a product rule in that way. Now, the interesting thing to note is that P1, P1 seems like an identity, but if we square it, we see it's P1, P1, which is equal to P1, which is equal to E, and it's just a point, but it's not a stationary point. It's an idempotent. It's a point which continuously rotates into itself. So a point is not something static, but continuously changing. And the interesting thing is that space emerges from the structure of idempotence. Now, I put in a caveat here. In the full theory, we really must go from Clifford algebras to von Neumann algebras. But that is a step that's too far, and I cannot go to that in this talk here. But we will keep everything simple, and we will just talk with Clifford algebras. Okay, remember, not objects, but as process or activity. Right, now then, How can we bring in addition? Because algebra requires two binary relations. I'm sorry, I'm not taking questions. I can see someone's asking me a question. I'm not stopping for it because I've got a lot to get through. So now what we have is we have a direction in the X and the Y, and we put them together. And before I define the right angles, just let me say, how do you get from this step to this step? By making the step from P1 to P2. And then what you find is that's automatically taken care of in the product. And then if we do it again, in other words, if we go from P2 and come back again to P1, we actually turn up with a minus sign, which means if we apply it twice, we get the arrow pointing in the opposite direction. And we've used this relationship here. So what we've got is an object which is squared producing the square root of unity. So we've got here a complex number, if you like, but it's a dynamic complex number. It is not an element of the complex field. If we, so the question that whenever I used to listen to Roger speak was, do we really need the complex field or the quaternions? And actually we need both. And that comes in very clearly in the biquaternions. Now let's have a look at the structure of the group structure in the Clifford algebras. Oh, this is just to show how fairly obvious how the exponential, the polar decomposition comes in the continuous case. We go from discrete steps to the continuous case of just going round in a circle. Okay, now let's go to the algebras. Now, what we've shown so far is the algebra of the complex number, which is CA, dotted on here. But the quaternions require two more objects. And you find that if you look at this, this is just the symbol FA that I was using, and it has a signature minus minus. So this one is plus minus minus minus. And I want to point out the local isomorphism here between SO3, because we've got three, this is a rotation group here. When you look at it in terms of this, you either look at the quaternions in terms of a split into these two or a split into a scalar and a three vector. In this case, you actually get SO3, and I want you to notice this. Local isomorphism is SP2. Now then, let's do the split quaternions. Again, the only difference is that these two objects are plus. So instead of having SO3, we have SO31, have SO2, but we still have the isomorphism between SP2. So the SP2, as it were, is sticking the quaternion and the split quaternion together. Okay, now let's go a bit further now, and let's see what the Clifford algebras, how many Clifford algebras do we have? Well, if these are the generators, then remember the Clifford algebra always, oh, sorry, that should be a plus sign. There's an anti-commutator, which gives you G mu nu, and G mu nu is diagonal with P plus ones and Q minus ones. And we've already seen that the signature is important, first of all, in distinguishing between the quaternion and the split quaternion. But it goes even further. And what I should point out here is I'm actually taking the Clifford algebra over the reals. And this was something that Dyson remarks about, a paper which I think people ought really to read. It's a very, very interesting paper. Right. Now then, there is only a finite number of Clifford algebras over the reals. And this is because of the Bott periodicity condition, that it closed under 8, you go up to R16 and you start all over again. Now, this table shows us how we've got a hierarchy of Clifford algebras. Now we'll see here is the quaternion. Here is R2. That's the two-dimensional matrices with real elements. That's two-dimensional matrices with complex elements and so on. And the way you build this table up is a very simple formula that the Clifford algebra of taking P up 1, Q up 1 is constructed via taking PQ and adding in the Clifford algebra C11. Okay, now I want to look at this. I found it very useful to look at this table upside down, as it were. And I took my my insight from Vaughan Jones's Tower of von Neumann algebras. And I was introduced to this tower by my friend Lou Kaufman, and he actually gets his knot polynomials out. So why has the von Neumann algebras got anything to do with knot polynomials? Very interesting question. But again, that's another story, and I mustn't go down that route. If we now look at the Tower of Clifford algebras presented in this way, we see that we slowly increase the number of generators. And as we increase the number of generators, we actually go up from the Schrödinger equation down here, the Bohm theory was quaternions here, the Pauli spin matrices come here, the Dirac spin matrices come in here. We've got in here the de Sitter, which is used quite a lot, but not in the main physics stream. And then I've stopped at the conformal. Why? Because the semi-spinners of the conformal are actually the twistors that Roger talks about. Okay. And then we can see how this fits in, the reals down the bottom, the reals down the bottom. We've then got the complex numbers, and so on. So we can see the relation between these two pictures. Nothing. How do we generate the geometry? I claimed somewhere along the line that we're going to use the algebras to generate the geometry. And what I've got here is an order of succession. Remember, I haven't got time specifically yet. I've just got an order of succession. So we start with my versor, which is the straight line, and we think a point on that versor. Now the versor develops into another versor. That's my step function from one versor to the other versor. But that's equivalent to x moving from 0 to some point t. And what I'm building here is this particular Clifford algebra in which ds squared is equal to minus dx squared. Now, let's use this formulae for constructing the higher algebra. What I have to do is I have to start with the line, which is that, and then I want to add this Clifford algebra to it, and that Clifford algebra is equivalent to adding t plus y and t minus y. So my metric now becomes a two-dimensional Minkowski metric. Here's the 2 dimensions of space and 1 dimension of time. So when I write it in terms of complex numbers, as we traditionally do, we get a left rotation and a right rotation. So this is just the flatland of Abbott. Now let's go one stage further. We now add C11 to the algebra that we've got here, the plane, and we form the Minkowski algebra with a t plus 1, a t plus z, t minus z, and what we get is the full Minkowski metric, which we then write as Dirac did in terms of Dirac light cone coordinates and the left and right. And then what we've actually constructed here is the light cone structure, where the t plus z is the forward light cone, t minus z is the backward light cone, and these two light cones, which are to do with the rotations, which We don't get a clear picture yet. It's only when we get to the twistors that we, to the conformal Clifford, that we get this relationship. And here are the various relations that you get from that. And then finally, and this is why I stopped in the my Clifford algebras at the conformal, is you build the conformal from the Minkowski space. You add tau plus lambda, tau minus lambda. And in fact, then what you find is you develop the conformal symmetry. And if in the algebraic approach, the Dirac, this algebra, the Clifford algebra, carries both the Dirac spinors and the twistors. And they're written in this particular form. You'll see left 1, right 1, left 2, right 2, left 2, right, sorry, left 1, right 2, left 2, right 1. And this translates into the motors. But that requires a good deal of work to actually show that. But I just wanted to bring the image up so that you could see how this is all fitting together. Okay, now we've dealt with the rotations, and that's all the literature. It's absolutely full of Clifford algebras with the rotation group. Now I want to say something about the amplitude, the step, because the step requires energy flow. And the energy flow consists, as we have seen, at least two parts. It's the linear momentum and the angular momentum. And just to remind you that the inertial energy actually has this remainder, which classically we throw away. Don't throw it away in quantum mechanics. So what we are dealing with then is how the rotator, what's the energy involved in the flow of the rotators? Now, the energy we want to bring in is the Hamiltonian flow. And this is where the symplectic group comes in. So the symplectic group comes in through Hamiltonian flow or mass flow or energy flow, and it introduces the idea of a symplectomorphism as opposed to a general diffeomorphism. So this is a special kind of diffeomorphism, and it's very important. The orthogonal geometry of space is the direct sum of orthogonal lines. The symplectic geometry is the direct sum of orthogonal hyperplanes. And this is all discussed beautifully in this book by Kromerol called Orthogonal and Symplectic Clifford Algebras. So what we need is both the orthogonal and the symplectic Clifford algebra. And if we look at that in terms of group structures, we're actually exploiting the relation between the orthogonal group in 2n dimensions over the reals and the symplectic group. And that gives us a subgroup of the unitary group. And that subgroup is the metaplectic group. Now, I want to mention the metaplectic group because that is what Morris is going to talk about in his talk. But let's see what happens, what we've done by combining the orthogonal and the symplectic. We've actually gone to the phase space. We've actually gone to a non-commutative phase space. Please forget what you've been taught. You cannot do phase space in quantum mechanics. If you allow a non-commutative phase space in the algebra, you can talk about phase space algebraically in quantum mechanics. Okay, so now what happens is the important thing is that in the space variables, the commutator is 0, whereas in the xp space, you get the Heisenberg relation. In the pxpy space, again, it's commutative. But remember, I've not put any quantum mechanics in this yet. This is still all classical mechanics. And there's a brilliant theorem by Gromov called the no-squeezing theorem, which Morris really taught me about. Very important for my talk in the sense that we are dealing with a non-commutative phase space in which we have the variables, the configuration X space and the configuration P space together. And remember, in quantum mechanics, you have a transformation, Fourier transformation between these two. So the structure in XY space has to be carried over into the structure in PY space. So what we're dealing with here is what I call orthosymplectic geometry. Although it's geometry, remember, it's actually photometry, but I won't go into that name because it's not well known in the English language. Okay. So now, where are we? What I want to do now is that I want to talk about a paper written by von Neumann in 1931. I mean, when I read it, it was only in German, and I struggled with translating it together with Fabio Foscura, who was working with me in Birkbeck at one stage, and we got together and did our best to translate von Neumann into and I was absolutely staggered by the paper. It was a totally different approach from his classic book, The Mathematical Foundations of Quantum Mechanics. And look, it was published a year before the German edition of the book. And in his 31 paper, he presents essentially the algebra I am discussing in the rest of this talk. As a result of this work, and as a result of the work that he did with Murray and von Neumann, he writes a letter to Birkhoff confessing that I may be saying something which is immoral, but I do not believe absolutely in Hilbert space anymore. Instead, he says, but I believe in the lattice of linear closed subspaces, which is really, what the hell does he mean by that? Well, actually, after a bit of digging, what one finds is that these linear closed subspaces are related to the primitive idempotence. And therefore, the idempotence again comes in. Remember, they're my points in my process space. The idempotence are already in the algebra that von Neumann was discussing. Now, unfortunately, we have a problem. And this is why the whole thing didn't develop the way von Neumann wanted it to, I believe. This is a conjecture. Whether it's true or not, we can debate. And the problem is that there are no idempotents in the Heisenberg algebra. It's a nilpotent algebra. And nilpotent means that there are no idempotents. But in the Clifford algebra, the orthogonal Clifford, there are hundreds of them. You fall over them at every turn. So how do we solve the problem? Well, von Neumann solved this problem by creating a star product, which is what I've been discussing in general terms. But it was already solved in a way which no one had realized by Dirac. He manufactured an idempotent by introducing the notion of a standard ket and a standard bra. And a standard ket is not the ordinary ket we use every day. It's a special ket. And in the X representation, you have a projection, you have the idempotent projecting into the X place. For the P representation, you have the P representation. So you're actually dealing with an algebraic approach. Dirac was dealing with the algebraic approach. And if you read his book, The Principles of Quantum Mechanics, you'll actually see it there if you know what you're looking for. And all of this is discussed brilliantly in his lectures in quantum mechanics and relativistic field theory, which was republished in 2012. The wave function now is not in this algebra at all, but it becomes all the information that is in the wave function is actually in an element of the left ideal of the algebra. In other words, the algebra was already carrying all the information you need for the wave function in the algebra itself. And because of that, the algebra evolves and there is no collapse of any wave function. The algebra automatically carries you through via the left ideal structure. Okay, so let's have a look at what von Neumann did. What he did was to show, first of all, that there was an isomorphism between the operator algebra and what he called the symbol algebra, A of Q and P. And Dirac called these objects C numbers, classical numbers. And these numbers are quantum numbers. They're the operators. They're the algebra of operators that we teach all our kids. Okay. So now how did he get the star product coming out? He replaced the operator A by alpha, B, beta, C, C. And then he says, all right, if I want to get the product of A, B to form C, how do I do it? I can write my C number alpha beta in terms of, and now we're integrating, notice we're integrating over the delta function. So we're generalizing the product that I used to introduce the whole idea. Now, the next step he does is he follows Weil and he introduces a U operator, which is alpha times the operator P, and VB is the operator Q with B as a coefficient, so that your non-commutativity relationship between the V's and the U's is in terms of an exponential. Now, this is very interesting because if you use here the nth root of unity, you get the quaternions, you get the nonions, you get the pions. There's a whole structure in the 1860s that was exploring this nth root of unity as your integrating factor there, as your factor there. And this is what gives rise to von Neumann algebras of type 1. But when you go to the continuum, you have to go to von Neumann algebras of type 2 and type 3. And it's not clear why von Neumann gave up he was arguing about the probability being not given completely in the algebra, discrete algebra, but it comes out naturally in the algebras of type 2. Okay, how does von Neumann do it? I've got to go through this quickly. It's a long paper, but I want to get the idea across. He replaces the operator by an integral over a weighting function. And the weighting function is in terms of the V and U operators. And then he shows that the star product of A times B, coming from up here, is this horrible thing here. And you cannot see this just by looking at it. It's quite a lengthy, probably over a page of working out in von Neumann's paper. But to my amazement, it turned out that this was just the Moyal product, which I'd been introduced in an entirely different way. And it leads to a commutation relation. In Moyal's hands, he calls alpha x and beta p over h bar, and you get immediately the Heisenberg uncertainty relation. But the man who showed this was really the Moyal product was a friend of mine who I met many, many years ago, a Dutchman called Jens Grunewald, who actually showed that the star product can be written in terms of these left operators and right operators. So we're now, you've seen this before in the Poisson bracket. Well, the Poisson bracket is actually the limit of the Moyal operator. It's the sine rather than the cosine, and you get another bracket coming out with a cosine. And what Moyal showed, that using the sine bracket, you get the Schrödinger equation emerging using a similar approach to that of David Bohm and his hidden variable work. Okay, let's try and see how this works now. Okay, so let's write any product at all can always be written as a sum and a difference. And we've got a Jordan product, and don't take all the Jordan language that you may have read about, the really nasty Jordan algebras. Just look at it as a Jordan product and a Lie product. And what the star product, we can form two types of bracket. A Baker bracket. Now, the reason why I call it a Baker bracket is the anti-commutator, and it was introduced to me by George Baker Jr. in 1958. Doesn't appear in the literature very often. It's in phys-rev, so it's okay. And we've got the Moyal bracket, which appears in many different places. And notice the Moyal bracket has got an H bar under it. So you've got to be careful. Don't put H bar equal to naught. Otherwise, everything blows up. Now, how do we apply this product to the quaternions? Well, we use the scalar vector splitting of the quaternion, and we get straight away that the Jordan product gives us the scalar part, and the Lie part gives us the rotor, the bivector. So this is directly leads to the mathematics of Clifford. Okay, now the important property of the brackets is that the Moyal bracket becomes the Poisson bracket to order H bar squared, whereas the Baker bracket simply becomes the straightforward product, again, to order H squared, and this is really the beginnings of deformation quantum mechanics. Okay. Now then, my claim is that I'm working with quantum mechanics in phase space. And I'm probably, some people are worried that you can't do that. Yes, you can. And in fact, a couple of Russians, Brezonin and Shubin, have got a whole book and a number of papers showing the relation between the Feynman propagator and a phase space propagator. And I want to use their results. I'll leave you to look up the way they do it. Very interesting, rather extensive, takes a lot of time. But you get a relation between the Feynman propagator in configuration space and the phase space propagator in phase space. And here's the opposite one. Okay, now then, now I'm going to use this propagator with my star product. That simply translates into this with the Grunewald relation. And we find that the other way around is we're working on X in this direction. Okay, so now if we work out what the Baker bracket is, we find it's the momentum times the propagator function, and the Moyal bracket turns out to be just simply the gradient of X. Notice that the gradient in X of the Baker bracket, of the propagator, of the phase space propagator. Okay. Now then, in order to make contact with configuration space, remember we're in phase space, we have to form the marginals. This is a well-known feature of statistical mechanics, that when you've got two variables, you form the marginals by integrating over one of the variables. So if we use the Moyal definition for the marginal momentum, P, it's an integral, it's the Baker bracket, and that gives me the density times the Moyal momentum. And in order to work that out, he shows that you can write it in terms of the usual Hilbert space approach. And he finds that the P double bar is in fact the gradient of the phase. And that's just the Bohm momentum in Bohm's simple theory. But there is another momentum, which is never mentioned, very rarely mentioned. And that comes from the Baker bracket. And that is known in Ed Nelson terms it the osmotic momentum, but in fact, it turns out, as we will see, to be the Coriolis momentum that I am talking about. Okay, so now let's have some pictures to try and make the whole thing seem a little bit less abstract. And this is the very nice work by Constantin Brioche and his co-workers, in which he uses these ideas to show how we can tie up the algebraic approach with the standard quantum mechanics. Because he starts with the wave function and then finds the momentum in configuration space is the gradient of the log of a psi, and that gives me the real part of being the Bohm momentum. The imaginary part is the osmotic momentum, and the Bohm momentum are these trajectories giving you this is a two-slit experiment, giving you the fringe pattern. The osmotic keeps the particles away and piles them up along the plateaus of the quantum potential for those people who have seen that quantum potential picture in Philippides, Dewdney, and myself. Okay, now he also shows brilliantly how the Coriolis momentum appears. They do an experiment, and the experiment is a circulating light beam, and you float a condensate, a particle. It's a condensate, and you allow it to couple to the angular momentum of the beam, the photon beam, and you take photographs of it 20 seconds, 40 seconds. So you can actually turn the whole thing round. So now when you draw your real part of the momentum, you can see it's the tangent velocity, whereas the imaginary part is the Coriolis term. And this is the term that gives rise to the Coriolis force. When you tell your kid running to jump on the roundabout for the first time, for God's sake, hold on, otherwise you're going to get thrown off. Okay. Now then, so that shows the two momentum, illustrates, I hope it gets the idea across fairly clearly. Now, because we've got a left multiplication and right multiplication, we have eigenvalues. They're called Stargenvalues. Not my name. And you have for the left multiplication, let's call this the energy is E1. The right multiplication, the energy is E2. So now, if we want the time development, we've got to carry that left and right translation into the probability density. And the way you do it is by operating dt on the wave function to begin with. For the other operations, operating on the complex conjugate of the wave function. Then if we take the differences, we get this equation, which in the limit is the classical Luvial equation. And if you take the sum, you find that you get this Janus product, Janus differential here, which corresponds actually to the Bohm energy. And you've got the anti-commutator Baker bracket here. And that gives rise to order of h bar to the Hamilton-Jacobi equation. If you go to the marginals and do the whole thing carefully, you find that the Baker bracket equation is equal sorry, the Moyal bracket, I'm sorry, my eyesight's not too good. The Moyal bracket gives you the lead product here, the commutator, gives you the quantum Liouville equation, whereas the Baker bracket is equivalent to the anti-commutator here. And if you choose this particular Hamiltonian, just to illustrate what's going on, you actually arrive at what David Bohm and I called the quantum Hamilton-Jacobi equation with the quantum potential already present in it. Okay, now I think just let's tie it up to really emphasize it is the Coriolis term that's coming into play here. Let's think classically for starters. With a particle moving in a central force, the Lagrangian is then written in the standard form, where gamma is this particular ratio here. And we find that the Euler-Lagrange equation, standard classical work, gives you this equation, and here is the Coriolis. Now, if you go to the Riemannian space-time, make it more general, what you find is the geodetic equation can be written in this form, and I have deliberately written it in a one-to-one correspondence with this form. This appears already in Weil's space-time matter, and U, by the way, is the full velocity. And what you find is that if you use the Minkowski coordinates, this equation very simply becomes this, and there's only one term with d mu, so there's only g naught naught, and the one term and the four derivatives there. You then go to a rotating coordinate system where your metric becomes this, and then you find that when you work out your Christoffel symbols, the only non-zero term is the mu equals 3 term, and that gives you the Coriolis force. And in this particular case, because of the metric we've chosen, the gamma is actually just equal to 2. And you can carry this even, so that shows that the Riemannian geometry is carrying the Coriolis momentum. To find the energy, all you have to do is to go to the energy momentum tensor and find the conservation of energy momentum using this. And this is done in Tolman's work, and you can see that the source of the quantum potential energy is in energy conservation. Okay. And there's the famous Mr. Tompkins in Wonderland, George Gomoff's book, which actually started me on my physics very many years ago. Now then, I want to just round off the story by referring to a paper I found just 2 years ago, which I have never seen referred to before in all the discussions about the quantum potential energy. And I read it for the first time in lockdown, and I was amazed to find that what DeWitt was doing quantum mechanics in a Riemannian space. And to do that, he showed that you had to replace your momentum operator, which is just the d by dx mu, by the d by dx mu plus an additional term coming from the Christoffel symbols. And in order to satisfy the principle of general covariance, now we're getting close to general relativity, the principle of general covariance, he showed that the Hamiltonian must take the form kinetic energy, an extra term proportional to h bar squared plus the classical potential. And he actually showed the Q, which he called the quantum potential, was given by this relation. And DeWitt concludes, and he makes one mistake: you don't let h bar go to 0, but please notice you have to take the covariant classical Hamiltonian and turn it into the covariant quantum Hamiltonian if you want a covariant theory. Extraordinary that this paper was in 2 issues later than the quantum potential paper, the hidden variable paper. Look, DeWitt actually uses the term quantum mechanical potential. And I have never seen anybody point out that he does this. Now, what DeWitt later does in a very complicated long paper in LaHouche lectures, he did this in the Reviews of Modern Physics. I learnt it from the LaHouche 1963 lectures, which I had a copy of. He showed that his Q was related to the density, mass density, times the Ricci scalar curvature. So you're connecting up the quantum potential, in quotes, with the scalar potential energy. There is a little bit of a problem here that it's the coefficient in front here is not uniquely defined, but we won't worry about that here. I also want to point out the historical note that in 1957, Feynman, Schwinger, and Wheeler discussed measuring this curvature, but decided at that time it was too small to detect. And whether that was the reason why it was never discussed again, I don't know. But now, before most of you joined us, I was having a private discussion, and we pointed out that in fact de Broglie was using the Riemannian geometry way back in 1928 in an appendix to his 1927 paper, which started the whole of de Broglie's approach to quantum mechanics. And what de Broglie showed was that under polar decomposition of the wave function, the Klein-Gordon equation with a mass m0 contained an extra term, h bar squared times D'Alembert of A, the quantum potential. And he wrote it like this, saying that what one's doing is one's rescaling the rest mass. And the rest mass rescaling means writing m0 squared, capital little m0 squared, plus this reaction term, the relativistic quantum potential energy. And combining this with, of course, DeWitt's result, you see that the mass is affected in some way by the scalar curvature. Now, at the same time, I remember reading Roger's work in the LaHouche lectures, cosmological discussions, where he writes for a zero rest mass Klein-Gordon equation, the equation is written like this. In other words, he's already using the quantum potential without realizing it. And just for completeness, the imaginary part of the Klein-Gordon equation becomes the continuity equation. Not important. Okay, now then, what's this got to do with conformal rescaling? Well, you can define the action in terms of m0 c ds squared. So changing m0 little to capital M0 is equivalent to a conformal transformation, that is going from a metric to another metric, and here is the conformal factor. The conformal factor is the ratio of capital M0 squared over little m0 squared. So what you find is, in fact, the quantum potential actually is involved in the rescaling. And I'm rather interesting. I haven't really had time to work this out, but I was reading Roger's book on cycles of time, and I'm finding that he's calling this omega, the omega I'm using here, the phantom field. and he comes in a cosmological context again. But it seems as if there's something coming out of just the Heisenberg picture in the very small. All the Heisenberg picture. And just to confirm it, I developed with Glenn Dennis a Dirac-Bohm picture, which is equivalent, which is unitary equivalent to the Heisenberg picture, and it appears in a disguised form in Dirac's Principle of Quantum Mechanics, but you've got to know where to look for it to find it. And in that picture, the wave function is replaced by a conformally related wave function, which doesn't have an amplitude to it. So we must rescale the wave function via, this is a standard rescaling technique that, again, I haven't had time to go through because we're getting towards the end of my hour now. And we find that, in fact, the scaling, the conformal factor, is just the amplitude of the wave function. So you actually see that the amplitude of the wave function is being related to the scalar curvature. Very interesting. So what is going on here? Okay. Well, I think that I've not done too badly with time as far as I can see. Good. Let me just draw some conclusions now before throwing it open. What I've tried to show is that by going to the Heisenberg picture, you find just one reality. The reality is the algebra of process. And here the operators are all time dependent, so that the dynamics is all in the algebra, the operator algebra. And both X and P develop together through the Heisenberg equations of motion. And this preserves the relation between the X representation and the P representation. If you just concentrate on the X representation and do things to that, you've got to ensure that what you do to the X representation also works in the P representation. Otherwise, quantum mechanics will not work. So what about the wave function? Where's the wave function? As I've said before, let me emphasize again, the information carried by the usual wave function is already encoded in the elements of the left ideal. And I should have had a reference to the papers of Bob Callaghan and myself, where we actually show this in great detail for the Pauli equation and the Dirac equation. So what happens is we allow the algebra to develop, then we project out the ideal using the primitive idempotent to find the final wave function. So the wave function doesn't evolve, it's the ideal structure that evolves. Second, the final point is that the algebraic description emphasized the notion of mass flow. All the early work in the 20s and 30s was about charge flow. But here we're talking about mass flow. And as Schrödinger pointed out in his paper on gauge invariance and the vacuum way back in 51, is that we can make mass flow look like a particle following a trajectory. And that will offer the explanation of why what I call the Mickey Mouse Bohm theory actually works. And what my approach here indicates is that it is possible to develop a geometrical description of quantum processes. This is something that Roger actually calls for. And my question I'm leaving is this particular approach that I've outlined here going to be any help in looking at quantum gravity? Okay, I've finished there. Thank you. thank you for listening.
Thank you. Michael, go ahead, please.
Well, thank you, Basil, for quite astonishing tour de force. I think we'll now throw this open to the floor, and I'm just trying to see who have. We use the usual convention of raised hands.
Can I go off the screen now so that I can see people asking me questions?
Yes, although it would be very helpful. I think people are almost bound to ask to refer to particular slides that you're.
All right, I can see hands up. Okay.
Yeah, you can. Good. Okay.
Yeah.
So, Jinder, do you want to actually single out which to call people? I can't quite see from here who had their hand up first.
Okay, I can handle it. Thanks, Basil. Thanks so much for a beautiful lecture. Really enjoyed it. So we open it up for questions. Tim, please go ahead. Do I need to unmute you? You're ready to go.
Okay. Hi, Basil. It's
Hi,
Tim Palmer here. How are you doing? Good. Nice to hear from you.
Yeah, I'm okay. I hope you're all right. We keep talking and then not talking.
I guess I wanted to ask you a little bit more about this DeWitt scalar curvature, because I have to confess I'm a little bit confused. You talk about it as Riemannian curvature in space-time, but the quantum potential is a potential in configuration space. And if you were talking about more than, if you were talking about two entangled particles, then isn't that going to lead to some horribly non-local, I don't even know how to think about it, sort of geometry if it's really space-time? I just wonder whether this geometry that DeWitt talks about is more a geometry in configure or even phase space rather than space-time. Is that possible?
I think it needs a lot more explanation, Tim. Please remember, I only discovered it about 2 or 3 years ago. And I was so shocked at the actual results that he was getting and trying to sort out exactly how he arrived at the curvature tensor that I can't really give you an authoritative answer on that.
Okay.
I think this is something which has to be talked about.
Yeah, no, it's certainly very
And
interesting. It's certainly extremely interesting.
Because I'm sorry, I'm as it were relatively new to that game, and I haven't thought it through properly. Because as you know, I'm not an high energy, I'm not a general relativistic theory man. My interests have always been in quantum mechanics, although my PhD, of course, was in solid state physics, but most of my research I did with David Bohm was in quantum mechanics.
Sure.
And although Roger was with us at Birkbeck in the early days, and I was always keeping my eye on GR, it was really studying Clifford algebras, etc., that I spent my time on.
No, I mean, I have a deep belief, I don't know if that's the right word, or hope at least, that there will be a geometric description of quantum mechanics, but not so much in space-time as in, say, something like the phase space that you talked about earlier. So that's where I would be keen to see whether DeWitt's ansatz, maybe it links more to a phase space geometry than a space-time geometry.
Yep, no, I agree with you, and I think that's something which I have been exploring and I could say something about, but not without preparation.
Yeah.
Because there's a lot of background that has to go into it, I'm afraid.
Okay. I'll shut up and let others
I hope I've said enough to interest people anyway.
Yeah, just a small clarification I request, Basil, on that. The DeWitt quantum potential is a different object from Bohm's quantum potential, because the DeWitt one would vanish in flat space-time, right?
It doesn't work that way.
Oh.
That's the whole point, you see, and people have often said, oh, no, it's if you got flat space-time, it's got, no, it doesn't. Because it's to do with the Coriolis force, and the Coriolis force is not in flat space-time, Tejinder.
Yes, I realize that. Yes, now, thank you.
I'm sorry, it's very surprising, but
Yes, it's like going to an accelerating frame in flat space-time kind of thing.
Absolutely spot on.
Yes.
That's the whole point. You're accelerating. It's a rotational acceleration.
Yes, I get that. Thank you. Bernd, please go ahead. I need to unmute you. Bernd, your hand. Bernd.
Thank you very much. I think I'm muted. I'm muted now. Professor Hiley, thank you very much for a wonderful and nice talk. I have a question concerning getting rid of the wave function, so to speak. Do you use the primitive idempotents as pure states and the non-primitive idempotents as mixed states? I think this was one of the earlier approaches when people...
I have concentrated on the pure state because I want to get it clear how the wave function comes in. When you go to the mixed state, you've then got to deal with it differently, but it's still in the algebra.
Okay, so what's it's the ideal which replaces the wave function. So the inner ideal is a kind of description for the state of a physical system.
Yes.
Okay, so
I mean, I'm sorry, I don't think I've got anything on my slides which show it, but there are a number of calculations that I've done which actually show that exactly how there is a one-to-one correspondence between the left ideal, the element of a left ideal, and the wave function. And you have to see that.
Okay, then I will
generalize it, and it goes
just
through.
have a look at your papers and maybe I will find it. The other thing is, so is it correct to conclude from DeWitt's paper that you need some kind of quantum potential like Bohm envisioned if you want to quantize gravity, if you want to keep general covariance? So it's just something you have to accept.
It's there, whether you like it or not. Why it's there?
Yeah, that's what I wanted to say. So it's something you cannot get around.
You can't get around. It's there.
So
What happens is, let me tell you clearly.
Yes.
What happens is that the general relativistic people have known it's there, but what they do is to introduce a notion of a natural coordinate system. And the natural coordinate system hides it.
Okay, so they have swept it under the carpet, but if you
They have swept it under the carpet.
And that's why it got lost. So, which is a little bit
because
unfortunate.
it's awkward. What's it doing there? I mean, when I first came across Bohm's work in, Bohmian mechanics work that became, unfortunately, Bohmian mechanics, the mystery for me was, what the hell was it doing there? It came out of the Schrödinger equation simply by polar decomposing the wave function. And you get this extra energy term. What the hell does it mean? Well, now we're beginning to see it's very deep. It's in the geometry. And I think we ought to bring it out and make it clear.
Okay,
and a lot more people ought to be talking about it to make it clear, and not hide it under the carpet. I'm sorry, I'm an old man, I'm an old man, so I can say what I like.
That's okay. The other thing, the one offer, if you need some help with papers written in German, I could help. I happen to be German, so maybe
yes, I know you happen to be German. And have you ever seen this 31 paper? Have you read the 31 paper?
Unfortunately not. This was new to me because I always try to get access to Annalen der Mathematik, but it's a little hard. So this somehow escaped me. But I'm very grateful to you.
You can get it on the internet. I've got the German paper.
Okay, then I will look this up. And if you have any questions concerning this, I could offer my help. Oh. And the last thing,
the idempotence he introduces by looking at Gaussians in the algebra.
Ah, okay.
So you have a phase-space Gaussian. That's a x squared plus p squared Gaussian. And then in order to come to the configuration space, you need the irreducible representation.
Ah, okay.
So you just suppress one of the p's, or you suppress the p representation and the q representation emerges, or the other way around. You suppress the q and the p representation emerges.
Okay, so
it's quite beautiful.
And one final remark, and then I give over to Claudio.
Yeah.
Did you, concerning the quantum potential, do you know about a paper from Weizsäcker from the 1930s, where I also introduced the quantum potential to describe nuclear physics processes?
Oh, yes, 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 I know
I think
that.
this was even earlier than Bohm and DeWitt. So basically, the quantum potential was discovered by Weizsäcker, but somehow he overlooked the importance. But okay.
And also, I think you'll find, please correct me if I'm wrong, that it's used in, what was it, in nuclear physics, was it? I
Yes.
can't remember. Yeah, it was used in nuclear physics, and it's still used there today.
Yes, yes, it is. It's still used as for nuclear physics calculation, which is also strange. Why don't nuclear physicists become Bohmians then? But yes,
Well,
you're right.
I don't blame them for not becoming Bohmians. I'd rather they look more at the Heisenberg picture.
Okay, I see. Okay, but
yeah, I think one of the problems has been that we have been trapped by the Schrödinger picture because it's so simple, until, of course, we get into all the problems. Collapses of wave functions, it's a
that's
catalog.
true. Basically, there was an attempt by Born and Jordan in 1930 to get people away from the Schrödinger picture. They wrote an entire textbook on quantum mechanics. It was the title, and they didn't mention any wave function.
That. Could you send me the reference on an email?
Yes, I can send you a reference. It's a textbook from 1930 written by Born and Jordan. It's just Quantenmechanik in German, so quantum mechanics, it's their whole title, and they don't mention the wave function and the whole book. It's just
please, I want that reference.
Okay, I will give you the reference, and I can also send you the PDF of the book if you like.
Oh, that's even better still, because I can't get into college these days at the moment.
Okay, then I will send you the reference and the book. But of course, it's all in German. It was unfortunately never translated into English. But
that doesn't matter. I'm okay with. I mean, I don't read German, but I can read it if I want to.
Okay, and now I'm done before Claudio gets angry about me. So
okay, Claudio, go ahead, please.
Yeah. So thanks for the talk. It's really interesting. I think I'll have to process a lot of it because it touches on some ideas I've been thinking a lot about lately. So one of the aspects, just in the end, you mentioned this conformal factor that comes in and so on.
Yeah.
Are you familiar with these whole ideas of modified measure theories?
No, I'm not.
Okay, so basically the idea is you take the Lagrangian, and instead of integrating against square root determinant G, you promote the measure to an independent degree of freedom. What that gives you is basically it solves the cosmological constant problem because it becomes a constant of integration.
Yeah.
And this was just a comment because this looks like the things you were showing there look quite similar. Second thing, regarding the conformal part, the Ricci scalar that comes out, it's actually if one quantizes the Maxwell equations accordingly in the same scheme, properly in curved spacetimes, then it's actually the Einstein tensor that pops out there.
Yeah.
So I don't know. I don't know how to make sense of that, but it's definitely if you do the quantization in curved spacetime properly, all these things do pop out. Yeah. And then there was a last question I actually had on, gosh, what was it? I forgot. Probably better let somebody else ask questions. I'll get back when I have my question again.
Thank you, Claudio. There's a comment from Igor that the first appearance of the quantum potential is probably Madelung 1926. You want to say something about it? Madelung? How do you say it?
No, I quite agree with. I'm well aware of Madelung's work, and in fact, the idea of fluids is very important. I think a paper a couple of years ago I wrote in which I brought out this connection between fluid dynamics and process dynamics. So I'm well aware of that, Jitendra.
Okay, great. Thank you. Tim, did you have a question?
Would Igor like to
Hello.
anything on that?
Oh.
If I unmute you? Or...
Yeah,
I had a quick. Sorry,
Sorry.
am I on or not? Sorry, I missed that.
No, go ahead, Tim.
Listen, I had a quick question to Basil. Sorry if I'm interrupting anything. I had a quick question. Basil, you mentioned it was quite near the beginning of your talk. You had some kind of dynamic operator, which you said was equivalent to a square root of -1.
Yes.
And then you sort of kind of embedded this somehow in the field of complex numbers. And then you introduced quaternions and all the rest of it. I'm just wondering, is there any kind of, let's call it a discrete version of your theory where these quantities aren't embedded in continuum fields? It's something, again, I feel intuitively, if one is looking for a sort of geometric approach, it's probably not going to be a continuum geometry, but something more discrete. And I just wonder if that's an avenue you've pursued at all.
Not that I've pursued it, but in fact, what I did look at, I did mention it very quickly, probably got lost in the rush through the whole topic. And that was when I had the UV equals e to the nth root of unity.
Right. Yep.
That is discrete.
Right. Yes, I
that takes us back to Sylvester in the 1850s when he investigated that particular structure.
Yes. I think that's very interesting. I think there could be some interesting consequences of that.
And I did play around with it, but I didn't get anywhere with it. It was extremely interesting. I mean, the nonions, which is the next one up from the quaternions, comes out, and that was very interesting. And whether that could be used in particle physics was something I played about with, but then abandoned it.
Yeah.
I'm afraid a lot of stuff I've abandoned on the way through.
Great,
So,
thank you.
But by the way, Basil, so the biquaternion algebra is the same as the Sedenian algebra, is it?
Oh, yes, yes.
Okay.
It's the Clifford algebra. It's the Clifford algebra. And you've got to be careful, Tajinder, with the Sedonian algebra, because the mathematicians call the Sedonians with minus signs all down the diagonal.
Okay.
The Dirac does not have all minus signs down the diagonal.
Okay.
And that makes all the difference. It makes a difference between an associative algebra and a non-associative algebra.
Okay. And just a related thing, early on in your talk, you had the Clifford algebra C24, which I think you got by adding the complex plane to 4D spacetime. Does that make it a 6D spacetime with 2 times?
You project. Yeah, no, but what you do is you project from the 6 space to the 4 space.
Okay, you wouldn't, this is a slightly off question, you wouldn't ascribe something physical reality to the 6D spacetime?
No, because something very interesting happens with the conformal group. And what happens is that, in fact, the algebra should be 8-dimensional, but it splits into two 4-dimensional algebras. And the twistors come out of the 4-dimensional algebra. That's the pictures that I drew with the matrices, R1, R2, L1, L2, etc. That came from that particular splitting of the algebra.
Okay, but what about the other 4-dimensional algebra?
Well, I don't explore it because it doesn't give you anything in terms of the light cone structure.
Yeah, but you know what I'm looking at these days, it probably these are 2 distinct 4-dimensional space-times, and we don't probably realize that our universe has another four-dimensional space-time, maybe which is microscopic, but we are looking at it. Have you had any thoughts on that at any stage?
No, it's certainly there to be exploited, but does it correspond to anything physical? I haven't.
Yeah. So what
looked
we are
at that.
looking at is that the geometry, the curvature geometry of that other 4D spacetime might actually be the weak force.
Absolutely, yeah. I haven't been down there at all.
Yeah, but you wouldn't rule it out a priori.
No, where the unitary symmetry fits in, I've got some ideas, but they're not very I am not convinced by them.
Okay.
Okay.
Because just few days back, I learned something else interesting, that, biquaternions are in a very natural way related to 6D Lorentz space-time with 3 times and 3 space.
Okay.
And
but-
that,
Tejinder, for me, the big question is, where does the notion of rest mass come from? And I have not seen it coming out of what I'm doing. Mass flow, yes. And the mass, inertial mass, gets this extra energy, the Coriolis energy, call it what you like. It's not quantum in particular. It's
yeah,
general energy.
So the idea there is that just as the electroweak theory is SU2L cross U1Y, what is actually gravitation is a SU2R cross a U1, call it something. We call it dark electromagnetism. And what mass, or more precisely square root of mass, is the analog of electric charge for this new U1 on the right-hand side. So if we really want to see origin of mass on the same footing as electric charge, we need another U1 gauge symmetry.
Yeah, but sorry, I'm interrupting. The
No,
trouble
go ahead.
is,
Go ahead.
when you've got the principle of equivalence, the rest mass doesn't behave like the charge.
Okay, so I can answer that.
Good.
In the other space-time, the electric charge seems to govern the equivalence principle, and the mass doesn't behave like charge. So this seems to be some kind of duality. Mass is not more special than charge. In the other 4D space-time, charge is more special than mass. We're just exploring.
Oh yeah,
just...
sure. No. There's a lot of exploring to be done.
Yeah. Okay, great. Thank you. I think I'll go to the
Can I,
chat.
sorry, Sujinder, could I just come in to say there's a very interesting observation posted by Igor Konachkov in the chat, which perhaps I could read out for Basil to get his reaction.
Yeah, please go ahead. Yeah.
Okay, I think this is Igor's posting in the chat. I think that the additional term in DeWitt's formulation, gamma mu, the contracted Christoffel symbol, added in the momentum operator in curved space-time, comes from the requirement of the consistency of its hermeticity with the scalar product in curved space-time, which includes the square root of minus g in the integration. Any reaction to that, Basil?
Oh, that's
very interesting observation, I think.
Yeah, no, that's absolutely true.
Oh,
I mean,
good.
I just didn't have time to go through it. That in actually deriving those equations, that's what you go through.
Right.
I mean, I just stuck down the results because I wanted to show that there was something there which might be worth looking at.
Yes. Well, it is very interesting. It certainly does lead us to think much more deeply about the role of the Christoffel symbols and what.
Okay, great. Thank you. So before I take Anthony's question, there's a question in the chat. Professor Basil, why did Dirac say that Schrödinger picture is equivalent to matrix mechanics? So I think they want your take on that.
Sorry, could you repeat the sentence again?
Dirac and probably others said that the Schrödinger picture is equivalent to Heisenberg's matrix mechanics, but you are probably saying they are not. Is that correct?
No, I'm saying be careful. What I'm basing my argument on is the Stone-von Neumann theorem. And I'm dealing with finite number of degrees of freedom, and I'm not dealing with an infinite number of degrees of freedom. That brings in a whole host of different questions. Okay? But with a finite number of degrees of freedom, what you show is that the Heisenberg picture and the Schrödinger picture are mathematically isomorphic. My question is, if things are mathematically isomorphic, does that necessarily imply that they are physically isomorphic? And the way I'm suggesting here is, no, they're not. You can get things out of the Heisenberg algebra that you cannot get out of the Schrödinger picture.
Okay. And does that also mean that when you say Heisenberg picture has only one reality, does that automatically take us to the Bohmian view of quantum mechanics?
Not automatically. What I did was to go to another picture, which is in Dirac, hidden away in Dirac's book. And that picture actually leads directly to the Bohm picture and has the quantum potential in it.
Okay, great. Thank you. Anthony, go ahead, please.
Hi, Basil.
Hi, Anthony.
Thanks very much for the talk. I just wanted to return to this question about the conformal term, the Ricci scalar in relation to the quantum potential, because I didn't quite understand what you're saying about how this could work even when you haven't got a curved background space, because we've got to consider the Coriolis term. And so you were saying, and Tejinder was saying that we go from non-rotating space to a rotating space that induces these terms. But of course, in doing that, it's still very much just a change in the connection you get, and can't be a change in true tensor quantities like the Ricci scalar. So that would still be zero in a rotating space. And so I was wondering how that would work in terms of what you want to happen there.
It's much more subtle than that, Anthony.
Okay.
What worried me, now how can I put this without going through another 20 minutes to talk? When you're looking at the covariant derivative, you find you cannot make a covariant derivative independent of the coordinate system. And you're always getting some extra terms coming in, which you try to hide under the carpet. And it's in that ambiguity that you get these extra terms coming in.
Okay, I can absolutely see that in a curved space-time that you get this extra term. That seems perfectly natural. But
this is all a flat space-time, but your geodesic is curved.
But I'm saying that in a flat space-time, even in a rotating frame where you get Coriolis and centrifugal forces, there is still no Ricci scalar.
Yeah.
I beg your pardon, but there is.
That's way too subtle, Basil, perhaps, yeah? In flat space time.
Oh God, yeah, okay, no, but this is very surprising. People are always talking to me about it, and I must get a proper answer for it. I don't have one at the moment, but I do know that if it's to do with intrinsic and extrinsic curvatures. And it's the proper discussion is in Thorne, Misner, and Wheeler's book, Gravitation. And you'll find they go into this where they get the intrinsic. Now, I'm always, is it intrinsic or extrinsic? It's the intrinsic, I think, which is the Coriolis force, and the extrinsic is what you're talking about, namely the curved space-time.
One thing I could think of, I don't know if it's related, is that in reality, there isn't a rotating frame which is always having the same angular velocity. At some stage you started it and some stage you'll stop it. And over there, there is, it's how to put it? You see what I'm saying? There is a gradient. I don't know if that has anything to do with inducing curvature at the end points.
No, you see, I think the real problem is, Mike, I think I'm going to have to introduce the idea of ferometry.
By all means, you can motivate that, I think, pretty straightforwardly.
No, I was reading Einstein.
It certainly bears on the whole question of intrinsic and extrinsic in geometry. So yeah, go ahead.
Yeah, I think that's where it is, but I'm just wondering whether the idea of process might be easier to get away from geometry, you see, because geometry fixes objects in space and time, whereas ferometry is about things developing in terms of actually nothing is an object as such, everything is a process. And certainly Einstein in his paper on über den Ether actually talks about ferometry there. It's quite an interesting idea that it's not the space that is, we're so obsessed with a curved space as existing a priori. It's the process that is curved.
Okay, so we're probably going a little beyond general relativity here.
Well, you see, it depends what you mean, but I'm going beyond what we're taught in general relativity. I'm not going beyond what I think Einstein was hinting at in general relativity.
Okay,
but then always the problem of a hint is whether you are being misled or not. You see, because you can see the problems. If you look at this scalar curvature as the geometry, what do we mean by having all these geometries all together with different curvatures in them?
Yeah. This was, if I can say so quickly, this, of course, was the problem which I was very much sensing when Roger, 2 weeks ago, produced his picture of the so-called quantum reality, the second of his two realities, and motivated in terms of the idea that intuitively one has to think of a superposition of partially formed, partially bifurcating geometries. But in what sense is something only partially formed and perhaps partially bifurcating, not is it quite clear what its status is with respect to those alternatives? In what sense is that a geometry? It's something in some sense pre-geometrical. It's ferometry.
It's the flowing movement.
Yeah. The term, I believe, originally comes from Leibniz, is it, or from?
It's a whole chapter in. No, I think it's Kant.
It was certainly used by Kant, but I'm not sure if he actually coined the term.
I don't know the history of it.
That's a one for the scholars. Let's get too far afield.
I'm not an expert in.
But it is. I mean, roughly speaking, the notion is that of an intrinsically dynamical geometry.
Yes.
I think
that's a beautiful way of putting it.
Anthony, you'd like to say something more?
I suppose only the point I think that was made by Tim Palmer at the beginning of the questions, that I still don't see how wanting this DeWitt term to tell us, okay, yes, there's definitely a quantum potential. Well, it's going to be totally different from the quantum potential that you have in the Bohm-Hiley approach, I would say, because the Bohm-Hiley approach, you get quantum potentials irrespective of any background curvature, irrespective of I would have thought, going to rotating frames. It's an intrinsic part of the description of ordinary quantum processes in ordinary flat space-time. And you need the quantum potential there to make it all work. Whereas here, we're looking at a tiny correction in something that is going to be, that quantum potential is going to be, I would have thought most of the time, extremely small compared to the quantum potential you need just to get the Bohm-Hiley approach to work.
If you mean that when you're dealing with mass flow, the quantum effect, the general relativity effect is very small, yes.
Yeah.
That's true. But that doesn't mean to say that this effect does not occur at the Bohm-Hiley theory, for example.
No, but I'm saying you've got a quantum potential which is going to be hugely bigger than this, which you need operating all the time.
And it's coming from the rotational degrees of freedom intrinsically.
Then we're back at the discussion before about how.
Yes, I know we're back at the discussion before,
okay.
and I don't know how to move on from that.
Okay.
I have moved on. If what you're saying is quite right, if you stick to a geometrical aspect, and here again I'm using geometrical in the traditional way, then it seems extraordinarily odd. But please if you read Weil's book, Space-Time Matter, you find there that he is actually saying that the curvature comes from the physical processes. He doesn't fix the time. And remember, he is the one who brings in the scale idea, which Einstein didn't agree with.
Yeah.
Right.
Okay.
So I think we've got
very much. It definitely gives us something to think about and look up and go back and read. I'll do that definitely. And at this juncture, Basil, could I ask you a more general question? Would you say the Bohm picture of quantum mechanics is superior to the collapse of the wave function picture? Why would you choose one over the other? I'm just for my curiosity about your.
Well, first of all, I think I remarked that the Bohm picture was Mickey Mouse. We know a lot of my colleagues get very angry with me when I say that. But I think it's a very simplistic approach to something much deeper. And therefore, I wouldn't prefer it over the collapse of the wave function. Oh, come on. How long have we been trying to solve the collapse of the wave function problem? 100 years or more. Are the people who have been working on it all that stupid that they cannot come up with an answer? I think the question is incorrect. And the question is because we are making an assumption. Where does the Schrödinger wave function, where does the Schrödinger equation come from, for goodness sake? If you read Feynman, he said it comes out of the head of Schrödinger, but that's not very interesting. You see, we accept the Schrödinger equation as something almost God-given, and then we work out all the consequences of it. But I don't see where it comes from. If you look at the Heisenberg approach, there is no Schrödinger picture there unless you come down to the story I've been trying to set out today, where finally you see it emerging in some limit as h bar, as you neglect higher terms of h bar squared.
Can I just?
Somehow, oh, sorry.
No, sorry, no, I didn't. I'm so sorry. I didn't mean to cut across what you were saying, Basil. I was just going to say, in the way that you're presenting it, particularly with your discussion of the way that the Schrödinger equation and the Schrödinger picture fits into the tower of Clifford algebras and the Bott periodicity, it seems one really has to think of the Schrödinger picture as just the tip of the iceberg, really.
Yeah.
It's the bit that we see above water, above these the much deeper water of this algebraic structure in the phase space. So
it's the top. It's the simplest algebra possible.
Yes.
It's at the top of the tower.
Yes. Well, yes. Well, the tip of the iceberg was my metaphor, but I think.
Yes, I know. I just turned it upside down.
Yeah, sure. No, I think. But I hope that gives some. Yes.
Professor Basil, out of my curiosity, I'm asking you a question that if non-locality doesn't exist, what will happen to Bohm in mechanics?
Sorry, if non-locality does not exist,
What would happen to Bohm mechanics?
well, first of all, I don't agree. I think Bohmian mechanics is a load of crap, if you don't mind me saying so bluntly on this program, on this series. Bohm never subscribed to Bohmian mechanics. In fact, I very nearly put a picture of myself in which
Or pilot
Wait,
wave
Jitu,
interpretation.
1 minute. Jitu, let
the
it
pilot
speak.
wave, we've move on, man, move on. That's something that happened in the 50s. We've moved a long way since then.
Can I
Now,
say,
if you-
Basil, I think the point about Bohm's 1952 paper was that it was essentially it was a response to a challenge. It was to produce a proof of concept that there could be a hidden variables theory, contrary to what people
sorry,
had
Mike,
argued.
Mike, could I just
Right.
say that there existed another interpretation of quantum mechanics?
Yes.
Because remember, when I grew up, I was always shouted out by Rudolf Biles, who said, "Why are you talking about interpretations? There's only one interpretation."
Which was the non-interpretation of the Copenhagen.
Which was the Copenhagen interpretation. So what David had to do was to produce
Yes.
a theory or an idea, a set of ideas, which showed there was an alternative way of explaining the quantum phenomena. And he came up with his particular approach, which he wrote in 52. You then read his book, Causality and Chance, and you'll find that he criticizes the approach quite severely and moves on to something much deeper, which was his idea of structure process.
Yeah, precisely because he didn't believe that the underlying theory could be mechanical.
Yeah,
But
not only mechanical, but the pilot wave was not sufficient to deal with all the problems we've got in quantum theory. That's just something which, if you don't want to worry about quantum mechanics, just use it. But I certainly wouldn't say, oh, this is the best thing since sliced bread. No, it's not.
So you would disagree with then the path followed, say, by Detlef Duer, Sheldon Goldstein?
Absolutely. I'm sorry. I've had I was thrown out of a pub nearly thrown out of a pub in Sweden, having an argument with Shelley Goldstein.
Yes, you must have got very heated indeed, Basil. But
I'm sorry.
Very interesting. Very interesting.
I do get heated.
But I do understand that David, I'm not putting, I hope I'm not putting words into his mouth, into yours, but I do recall you telling me that at one point David said very precisely, why do they insist on putting this label Bohmian mechanics on my viewpoint? The whole point is that my view is precisely not a mechanical theory.
No, what he said was, have they not read any of my work?
Yeah. Well, the trouble is, other than the 1952 paper, it seems not. That's the problem.
Well,
there's all this later work that he did in connection with the quantum potential. They simply ignore or treat it as a pure hand waving, which is.
And I used to get really shouted at for talking about the quantum potential. It doesn't exist. It's a myth. It's got nothing to do with reality. I'm sorry, that's me suffering as a youngster.
Yeah. By the way, speaking about youngsters suffering, I think Jithu still has an additional question he'd like to know. Before he speaks, could I perhaps say, Jithu, I think you spoke, didn't you, last week after 2 weeks ago after Roger's talk. Jithu, I think I'm right in saying is a high school student.
Yeah, that's true. He's the youngest, much younger. He's 17.
Yeah, he's a very young man. He's, I think, only 17 years of age. So you know, don't start beating up on him because he has some very bright spark questions. Jithu, please do go ahead and I'll ask your follow-up question.
Professor Basil, thanks for giving this wonderful lecture. But I have a question that you are talking about the Rasmus, and I have understood from your lecture that you are unable to understand the Rasmus notion in that picture of Coriolis force in that curved spacetime. Is that you meaning?
No, I'm very puzzled about the where
Yeah,
the
I
come
think
from in
it's
the
because
first
of
place.
the unknown.
Jitu, one important rule: when the other person's speaking, you have to wait.
Okay, fine.
Please wait.
Okay, go on. Sorry, I was just saying I've not got your point, so make your point clear.
I think it's because of the unknown nature of inertia, like Dennis Sciama pointed out in his Origin of Inertia paper. Like we need some more fundamental theory, like a paradigm to explain, to integrate the inertial forces into the quantum theory. Like,
Yeah, I agree. And that's another way of putting what my worry is when I'm talking about the rest. But you see, I used to work in the high energy field with all the groups, the algebra groups that were trying to fit the elementary particles. I grew up in that atmosphere. And the trouble was there was never a clear reason for the existence of a mass spectrum.
Yeah.
And you then had to take everything and say, we've got an internal degrees of freedom and we've got external degrees of freedom. And we treated all the internal degrees of freedom as the isospin, the changeness, all the modern stuff that's come from that. And I don't like that way. Like, is that the right word I should be using? I feel it's all one structure and not a direct product of two independent structures.
I agree, Basil. I agree. Yes.
But I don't know how, but that's just crying out in the dark because I don't know how to do it.
Yeah, I think, like I mentioned, I think there is another gauge symmetry whose quantum number is mass or square root of mass. We need such a gauge symmetry.
Yeah, well, I mean, I've cut out the gauge symmetry because I had to get it down to 1 hour. But there's another hour I can give on gauge symmetry.
Okay, great. Okay, thank you.
But we won't do it now.
Yeah, I think. I'm waiting to see if there are any more questions. Otherwise, we are anyway reaching the winding up time. We have 8 more minutes. And yeah, Bernd, please go ahead. I need yes, go ahead.
It will just be a brief question concerning the work of Weil. In your model, do you use the Riemannian geometry or Weil geometry?
Get me clear. I said that De Broglie and DeWitt used Riemannian geometry.
Yes.
But what I didn't go on to do was to actually use Weil geometry. And that's what you can do.
You can do, but this is something for, well, still to
I
be
haven't
done.
mentioned in here, but I didn't because I haven't got the final conclusion that would fit in nicely in the hour that I was given.
I see. So this is a work in progress.
It's work in progress. Yes.
Okay. Because this could clear up some of the confusion concerning why you still have Ricci scalar and flat spacetime, because this is different in Weil geometry than in Riemannian geometry.
In what sense could you explain? Could you explain why you're saying that?
Well, because Weil geometry is has a kind of non-metricity, and in this case, you cannot put a flat coordinate system to a point. It's the whole point of non-metricity.
Oh, okay.
And the point about Riemannian geometry is that you can attach a flat coordinate system at least to one point, and basically to any point. You can transform away curvature and the gravitational field. And Weil geometry was one of the first examples of a geometry which has non-metricity. And in this case, this is no longer possible. You cannot attach a flat coordinate system to any point.
Right.
So you can. This could be, maybe this is an
I
explanation.
think you're probably onto something there, which I must think about. Thank you. Thank you for that comment.
You're welcome.
Yeah, there's a comment from Igor. Guts go beyond the direct product symmetry group of the standard model. That's a comment from Igor. If you want to respond to that, grand unified theories go beyond the direct product symmetry group of the standard.
I haven't. Yeah, I haven't studied those, Tajinder, so I won't say anything.
Okay, thanks. So one other question I had, Basil, correct me if I'm wrong. We can say from the macroscopic world that we don't see position superpositions. We don't see a macroscopic object in two places at the same time, and that's a puzzle. And that statement maybe I can make independent of the Schrödinger equation. How do we handle this in the Heisenberg picture of reality?
You'd never see two objects in different positions, macroscopic objects.
Yes, I see that. Yes.
Yeah, because you see,
yes.
I've shown that when you take the equations of the Heisenberg in terms of the deformation algebra, you don't get two objects in linear superposition. It doesn't arise.
Yes, I missed that. Yes, you are right. I agree. Yes. Yeah, it's all tied up with the wave function mindset. I see that now. Yes.
Yeah, if you take the wave function as the reality, you will always get into trouble. Yes. We've been getting into trouble for 100 years over it.
Just not a question, a remark. Do you know about, for Neumann, when he said he no longer believed in Hilbert spaces, he was developing his own kind of projective geometries called continuous geometries.
Yes.
In an attempt to go beyond quantum theory. I think it did not work out because his generalized geometries were not invariant with respect to the Lorentz group. But there was inspired by von Neumann, there was always a kind of crosstalk between von Neumann and Jordan. Jordan also tried to reformulate or extend quantum theory by developing a generalization of projective geometries, and he also started with the idea, I use idempotence as the primitive notion for states, and also for as a primitive notion for geometry. So the primitive idempotence are the points, and the non-primitive are the lines, and he tried to start with the very foundations of projective geometry to develop a kind of, replacement of Hilbert space, so to speak, and to go beyond quantum theory. And this was also based on his idea to go beyond, traditional quantum logic. This was also something which was introduced by von Neumann and Birkhoff in the 1930s.
That's right, yeah.
And von Neumann tried to, and they showed that certain, lattices are isomorphic to projective geometries. And Jordan then tried to use this as a starting point to go beyond quantum theory or to reformulate quantum theory. And interestingly, there's a link between Bohm and Jordan. They started to question the linearity of expectation value axiom, which von Neumann introduced in 1931 to exclude hidden variables. So this was one of the starting points of his axiomatics of quantum theory, that expectation values have to be linear. And surprisingly, at the same time Bohm was questioning this axiom, Jordan did the same, and he tried to develop theories or also geometries where this is no longer valid. And he even wrote to von Neumann a letter. He wrote a letter to von Neumann and asked von Neumann, is this axiom really necessary? Because I have ideas where I need to drop this axiom, but I don't know whether there was any answer by von Neumann to this.
Okay, no, I've never discussed that with him. But one thing that is clear recently is the work of Haag. Maybe you know Rudolf Haag.
Mm-hmm.
Yes.
And they're actually moving to the type 3 von Neumann algebras. And they seem to be extremely exciting. There's the work by Rovelli and Alan Kohn on time emerging, the dynamics emerging from the von Neumann algebras of type 3.
Mm-hmm.
They're very, very tricky mathematical devices to get your head round.
Mm.
But there is something that I think is worth spending time on and developing.
Yeah. Well, yeah. Basil, would you say that, yes, we can keep on talking about understanding quantum mechanics, but unless there comes forth an experiment which disagrees with quantum mechanics, we are all going to keep talking about different ways of understanding the theory.
Well, for me, the problem is how do we bring general relativity and quantum mechanics together? That's what Roger Penrose's argument was all about. And I think that's still, I started, because remember, I actually was at Birkbeck starting with David Bohm when he got the chair there, and there was Roger Penrose in the maths department, and we held seminars regularly. And he was developing his twistor theory, and that's why I know a little bit about twistor theory, because I was there when it was actually being formed. Okay.
Okay. I get your picture. You're saying, all right, I don't have an experiment with this which disagrees with quantum theory, but I still have a problem at hand, how to put together general relativity and quantum mechanics. And maybe we need to look at quantum mechanics in a certain way to make progress along this so-called quantum gravity problem.
Yeah,
I think that's your picture.
But remember, Tajinder, one of the handicaps of COVID was that we actually had a group of us at University College with Rob Flack and Vincenzo Moricelli. And what we found was that we were looking for experimental evidence of this extra potential. It turned out that if we looked at the weak values and measured weak values, the weak values were related to the osmotic momentum or the Coriolis momentum, whatever we want to call it. But unfortunately, we got locked out of the laboratory and we could not continue. And of course, you know what happens if we've got people employed, the money runs out without any satisfactory experimental work being done. And I'm afraid we got really...
Yeah, I get that. But isn't someone willing to get back to that experiment?
We no longer have any money, Tajinder.
Yeah, but others, you think you're not, others have not yet gotten interested in other groups or other researchers.
No, unfortunately, I mean, there are people at University College who are trying to get people interested because they think it is important what we were trying to do.
I know
And
Peter Barker.
The apparatus is there. The apparatus is there. We spent about £1 million on the apparatus, and it's just lying there, collecting dust.
Do you know Peter Barker at University College?
Well, he's part of the team.
Oh, well, he can do it.
Yeah, but he's part of the team, and in fact, we pinched his apparatus to do some of our work.
Okay.
I should say borrowed, actually, but no, he was willing to allow this particular piece of apparatus to be used. He was one of the leaders of our group. And in fact, we had during lockdown, we did manage to find a Dirac method of measuring magnetic fields, which we were going to use, but we ran out of money.
Yeah. Another interesting thing might be what Detlef Duer and Siddhant Das were doing, arrival times. I don't understand the details. But
yeah, sorry, Tajinder, I'm interrupting you again. I'm very bad-mannered.
I
worked on that arrival times with, Rick, what was his name in Canada? He's unfortunately passed on now. Levins. I think it was Rick Levins. And we had a long discussion. I was with him for a year in Canada working on this. And the trouble is the time doesn't fit in properly with what we're doing here. I never got a clear answer on this.
Mhm.
So I'm sorry, once again, but doesn't mean to say other people shouldn't try.
Yeah, so Siddhant will be talking on it later in this series, so maybe we can have a discussion between you and him.
Yeah.
He was with Detlef Duer. He was Detlef's student, I think.
Okay. Yes, I'm afraid I didn't.
Yes, he was. He
No,
was a
I'm not going to
student,
say
yes.
any more because this is being recorded.
Yeah, okay. All right, so are there more questions of Michael? We should wind up now.
It's entirely for you and for Basil to say if you
Well,
want
I
to
would very
continue.
much like to wind up now, Mike. because
Okay, in
I
that
am-
case, we'll go with that. And
I'm an old man.
well,
But-
so keep reminding us, but I have to say,
No,
you certainly haven't shown much evidence of it this evening.
Yeah, it's such a brilliant talk.
Yes.
If someone looked at the slides, they won't know your age. But
It was an absolutely wonderful talk, covering an enormous amount of ground, and as I say, certainly raising some very, very interesting
very
questions in
proud
the
to
discussion.
record it. Yeah, the recordings are a treasure.
Yes, I think so too.
Good. I'm glad. I'm glad you enjoyed it.
We hope to get them up very soon. And we also hope to have Roger's talk from last week restored to the playlist very soon as well. So I'll just thank Basil again. I was actually going to pass a comment about the Stone-von Neumann theorem in connection with my own interest in the development of algebraic geometry in the 20th century, because it was a very key landmark, the whole idea that the structure of geometries should be thought of in terms of their ideals, and the way that the ideals transform, as I say, it was a more fruitful way than in thinking in terms of structure imposed on an underlying set of points, and has been quite crucial in the overall development of algebraic geometry.
This will take us into category theory.
Yes, I know, because exactly what I was hoping you were going to say, which is subject for another day.
Yes, precisely. That's why I didn't say it.
But it just shows how vast the range of interconnections that are raised by this work is. So can I say thank you again, not just to Basil, but to all of the people who've contributed, and indeed all the people just for being here, including the people who just contributed comments in the chat, some of which were extremely interesting and illuminating. And we will see you. Can I just remind everybody that our next talk is in fact in a week's time. We're not having the usual gap of 2 weeks between sessions of the seminar this time, for various reasons. We're going to have the next talk on Friday, the 8th of March, when Maurice de Gosson will be talking to us about the symplectomorphisms and quantum blobs and the Gromov squeezing theorem and some of the other things, the metaplectic group and other topics, some of which Basil has mentioned today. And then we will have a gap until the 22nd of March, because unfortunately our speaker for the 15th of March has had to fall out. So that's going to be Maurice de Gosson on the 8th.
29th, Michael. 29th.
Sorry, 20. I beg your pardon. Sorry, Tajindam. I stand corrected. Sorry. So it'll be Maurice de Gosson next week on the 8th, and then there will be a gap until the 29th. And we hope very much to see you all back on both of those occasions.
Yeah, just one last thing, Michael. I've been asked again what happened to Roger's talk. So I've been telling people that please hang on, it'll be back. Yeah. So I think just letting everybody know.
What happened to Roger's talk briefly was that there was an issue to do with the signature of the release, confirming that his permission to allow it to be posted, which his PA will deal with. And I hope that by the time we're back here to hear Maurice's talk, with luck, it will be back again on the site. It's a technical issue to do with the legal status of copyright releases, which we need to deal with. But please believe me, we will do our best to make sure that it's back before next week.
Great, thanks, Michael. Thanks. That was very helpful. So.
Okay, well, can I just say thanks for listening to everybody? I hope they found something interesting.
Yeah,
I think we all found a lot of very interesting things indeed, Basil.
Absolutely brilliant. Yeah.
Yes, it was great fun. Thank you to everybody once again, and we'll see you all hopefully in a week's time. Cheerio.
Bye-bye.
Bye-bye to everyone.
Bye.
Thanks to all.